So, to recap what we have done in the last 4 weeks, in a sense, we took the perspective of the adversary. Right? So we said at the beginning of the semester that we would have like a first section of the course will be attacks, the second will be privacy-preserving mechanisms, and the third will be combining the two in privacy-preserving machine learning and more advanced techniques. So we had specific attacks for specific privacy-preserving techniques, such as k-anonymity. We had general attacks, such as reconstruction. We had, through the strongest possible attack we can imagine, which is essentially membership inference under full knowledge of the adversary, we developed a privacy notion that turned out to be differential privacy. And since that privacy notion takes its definition from some imaginary attack, we also define auditing, privacy auditing, which is an empirical lower bounding of that privacy parameter. Okay. So now we will move on in this section to privacy preserving machine learning. Now, since you took some differential privacy basic course, you might ask yourself, what am I going to do here? You already met the Laplace mechanism, the Gaussian mechanism, the exponential mechanism, a few of those building blocks. And one of the things I can do, and we will do in later weeks, is introduce new algorithms that are much more sophisticated, even though in many cases you will realize that they are also just the base mechanisms combined in a smarter way. But this week I will still focus on doing the very basic task of estimating some very basic quantities, and realize that even doing those things that at first glance you would say, oh, that part we already know how to do, turns out to be much more subtle and much more complex in many cases. So to remind you, in the first week, we took as a running example some data set from the census. It's called Fulton. It's a PUMS, a microdata set of some public data, and it consists of a CSV effectively. It has a bunch of parameters. One of them is salary, and in these few lectures, we will now ask ourselves just how can I learn in a private manner something about the salary. So let's say I would like to learn something like a predictor of the salary as a function of the other parameters of the sex and age and number of children and whatever. But for now, this week we will even lower the bar and just start with the most basic thing, which will run throughout this lecture, which is just like, what's going on with the salary as it's on its own? Like, what is the range? What are the numbers? Like, you come with some prior, right? You know, I mean, you maybe don't know exactly what is the distribution of salaries in the US. Maybe you don't know, this is not from this year. This is, I think, from 2010. So there was some inflation. We have some general idea, but let's assume for now we know nothing. And so here's the true distribution of the full data. This is like the secret thing that as statisticians we don't know and we want to learn from. Therefore, we would not be able to assume later anything like, oh, I see that the maximum value is something, so therefore, no. So let's just understand this plot. So it's sort of an inverted histogram visually, but it should be interpreted in the following way. When you have a data set that is that consists of real numbers, you can show it as a sort of as a CDF in a way. So basically, I took all the values and I sorted them in increasing order from left to right. So that's what you see. So here are the people that have zero salary, I mean, some people don't have income. And here we have, you can't even see, but there is like a tiny, tiny column that gets all the way to, what is the maximum value? 717. This is like, there's one person with this annual income. Okay, this is just to give you a sense of sort of the distribution in a way, but we typically look at it the other way around. We look at it as a histogram. So now the x-axis is the histogram, the annual income, and it's binned with some width, and this is the distribution. Okay, this is just so we have a sense of what's going on. So as you can see, the majority of people earn up to, I don't know, 30,000, I would say, and then by the time you get to 100,000, you covered 90-something%, and so on. Okay, but you have a few in over 300,000. Right, this is the setting. So, before I can hope to achieve something like predicting a salary of a person by their other features based on my data set, I would probably want, as a statistician, to just get a very general sense of the data, of having some kind of information of this type. So perhaps the most basic question I might ask is, what's the average salary in this data set? So how would I do it?
Average, not median.
Sorry?
Average. Not
Average,
median.
for now. That's typically the first question we ask.
Well, so when they're having bracket, you would set the average for its bracket.
No bracket. The average of the full data set. There's one number per person, and just one the average.
And divide.
Yeah, that's the non-private one. How do I do it privately?
Add some noise afterwards.
Okay. How much noise? So just to have a running example, from now on, I would always assume my sample, I will treat this as the true distribution, the entire population, and I would assume I sampled 1,000 people out of this distribution. It's always going to be 1,000, and I want to maintain, let's say, epsilon equal 1. That will be right. I could always say something like, oh, I want a certain accuracy, and therefore what kind of privacy I would get. But to simplify things, I would say I want to fix epsilon equal 1. How much noise do I need to add? So how do I do that?
Depends on the sensitivity, which depends on the range.
Exactly. So if we don't know the range, you really truly don't know, then we just cannot provide privacy. If someone might earn $1 trillion a year, so $1 trillion divided by 1,000 is still $1 billion, and I need to add noise that scales with, like, give or take $1 billion over epsilon, which is $1 billion. It's way above everything here, so it's useless. So now, okay, so I can continue just saying I can't, but something that would give us sort of a more natural baseline is, let's say I have a cap that I can either assume, which is okay if you somehow know, but the more relevant is I can always clip the data to that range, so I can also enforce it. So obviously saying, well, I know exactly, here, I would cap it here because this is where most of the data is, not fair. So I chose the number 10 million, which is like significantly above the range, but not like unreasonably above the range. So we have this as a rule of thumb of saying, let's say we, as the data analysts, have some very general prior that tells us that, look, it can't be that crazy. But that prior is not good enough to basically say, oh, we already know the range of the data. So 10 million, that's what I chose.
Look at the average based on the median. Would that be more legitimate because the median is actually relatively private?
We will get to the question of median, and your assumption that the median is relatively private is a tricky one at its own. But we'll get there. Let's do it step by step. No, so that's step by step. This is, we'll get to the median. We're starting with the average.
I would know using the median, assuming the median is private. Using that.
No, okay, so wait. That's combining pieces of information in order to create better algorithms. This is basically the subject of this lecture, but here's the deal. A good, useful algorithm doesn't assume anything. So you're starting really from a either blank slate or like nearly blank. So here, you see, I assume one thing. I know the 10 million number, but like I explicitly chose a number that's large enough that it's not like I really know what's going on in the data. Okay, so this is what happens. We see here three distributions. In a moment, I'll explain why there are three, even though you see only two. That will be sort of the baseline of the way we look at things. If I fix the number of users, elements in the data, in the subsets that I sampled, 1,000, and I fixed epsilon, and I add epsilon equal 1, and I add the amount of noise required in order to release the mean in a epsilon, and I fix some delta, I don't know, 10 to the minus 10 or something. I'm using Gaussian mechanism here throughout. Then this is what would happen. So we have three gaps we could naturally think of. One is, what is the distribution of the gap between the empirical mean and the true mean? This is the statistical error. And that is the black line. Then we have the sample accuracy of the mechanism, meaning typically how far is the output of the mechanism from the true empirical value. And the third is, the one we really care about, is how far is the output of the mechanism from the true value of the underlying distribution that we care about. So as you can see, the typical, the standard deviation of the data of the 1,000 elements is 1.9, and the standard deviation of the added noise is 18. So for all intents and purposes, we completely masked the signal. This is a useless piece of information. Okay, so that 1.9 should serve, in the typical case, as sort of a rule of thumb of this is the scale of the noise that is reasonable. 1.9 is what the statistician suffers even if there was no privacy, just because they had access to a particular data set out of the distribution and not to the full distribution. Okay? And we never access the underlying distribution, except in a sense the census is a weird case, because the full census, not the surveys that the Bureau runs, is in a way access to the full distribution. They're supposed to interview nearly everyone. It's nearly an area, but like for all intents and purposes, it's practically everyone. So the census itself is not really a survey. But for simplicity, we're thinking about surveys, not about the census. Okay, so 1.9 in this particular example is what the statistician suffers. So if privacy adds something that's significantly lower, let's say 0.1 or 0.2, then the statistician should say, they don't always say because it might confuse them, but should say, okay, it's equivalent to basically somewhat decreasing my sample size, that's fine. And if it increases it by about 2, then it's non-negligible but still manageable, right? It's sort of equivalent to what would happen had you just divided your sample size by 2. Square root of 2. And when you have 20, nearly 20 like we have here, this is basically a useless signal.
Is it basically dividing your data set by like 500 or something like that?
Yes, but okay, that's right. If you say that for privacy I need to sacrifice some small constant fraction, that's fine. If it's a huge constant fraction, then it's no longer fine.
Depending on your database size, but yeah.
Sorry?
Depending on your database size.
Right, so I'm saying, in this setting, this is a regime. We're just doing the Gaussian, like in the base course, we learned that computing the mean or the sum is a solved problem. And the first moment you try to use it on something from the real world, you realize, not really. Okay, so of course I can, settle for a higher value of epsilon, sample more data, but this feels like a very wasteful analysis. Like, we saw the data. Like, nearly none of the elements have an effect that's even remotely close to 10 million divided by whatever is the sample size. So we should be able to do better. Okay, so here's my first attempt. We know that when you compute the average over n IID sampled elements, the distribution of the average is, give or take, approaching a Gaussian. Okay. So let's do the following thing. Let's estimate privately the mean by truncating. Truncating to what? To, let's say, the empirical mean plus minus some number of standard deviations. So with this example, I chose 4, but whatever, that's a hyperparameter. Okay, so here's the idea. We take the mean, we take the standard deviation, empirical ones, both of them. We define the range that is the mean plus minus 4 times, in this example, the standard deviation. Truncate the data to that, and then add noise that's scaled, that's with this range. Okay? Is this private?
Definitely not epsilon delta. Or definitely not pure epsilon.
So I'm doing Gaussian mechanism, so I don't care at all about.
You have data sets that are somewhat far apart. There's a slice where one can end up in that the other one can't end up in. But for the Gaussian, they can and every year they can both theoretically end up. It's just that the delta ends up being very.
So wait, I will stop you there because notice that you made a good point, and then you combine it with another point that is also valid but in a different axis. So the delta covers events in the distribution of outputs given a data set. Delta, intuitively speaking, says I'm willing to accept an event where the privacy loss exceeds epsilon as long as its probability is small enough, captured about by delta. Right? It's not exactly, but it's up to factors. This is a correct interpretation. The distribution over data sets is not part of this language. The quantifier that privacy has for data sets is not distributional, but for all. So if you think you have a counterexample of a data set that's very sensitive, then it's not a problem of, oh, is your delta large enough to cover it? It's that you're doomed. Okay, so there's a good point. So let's start with a basic example. What happens if I have 2 neighboring data sets that differ by an element, like the element that we changed does have a very large value, but the rest of the data set was actually sampled uniformly from the distribution. So again, I'm showing the data sets in the way I showed it before. This is not the histogram, but like the actual values. So let's see what happens. The mean has changed by a little bit, by the 3rd digit, and the range. So the range here would always be, it's the mean plus minus 4 times standard deviation, but it's asymmetric because salaries are non-negative. So you always truncate below by 0. I mean, you don't need to truncate by 0 because it's never negative. So basically, the truncation is one-sided. So what is it? It's also like the 3rd digit change. Like for all intents and purposes, it did not. Wait, I will increase the font. Yes, this is better. I sent it to you, by the way. You should be able to access it. Hopefully, in this one, I hope will run also on your browser. Anyway, so for a typical example, this truncation will indeed be relatively stable, and then everything is okay, even if your one element is extreme. So in some sense, had we accepted a privacy notion that has a for all quantifier for the element, but with high probability quantifier on the rest of the data set, and we had some distributional assumptions, then this proposal is private. But this is not the definition we choose. And this is the what we remember from last lecture. This is the two distributions that are induced. These are two means that, as you see, the centers are now, instead of being in 0 and 1, are in some like crazy number, 32,000 something, but it doesn't matter. What matters is only the gap between the two. So if the gap is 1 or 5 or whatever, that's what matters. So we have a trade-off, and we have the slope that defines epsilon, and then we see, what is it? We need to add standard deviation, that's 4.7, okay? If I know the average salary in a country up to $4.7, I'm fine. No one will care for that. No one will complain, okay? So this would have been good. But here's another possible data set. And again, you can see here that one element that drives everything crazy, but for a large enough element, it will not only change the mean, it will also change the standard deviation. So now we have two data sets whose mean differ by 2 point something, but the standard deviation has an even bigger gap. And now we have this weird thing where we're comparing two more interesting distributions. So before I scroll down, let's think together. What kind of two distributions will I see below instead of these two? So these two were two Gaussians, practically the same variance, mean shifted by 2.5, because that was the value that correspond to the effect of that single element. What is the
one to the right would be more smushed down and smeared out, basically.
You're giving me a visual description, but we know which distributions are these, so we even know to say what kind of let's start. Which family of distributions they will be?
Still Gaussians.
Both of them are Gaussians, right? Because there's no distributional aspect of these. I'm not asking you what is the distribution of the estimated value where the distribution is defined both over sampling and over the noise addition. Like this is a particular data set, this is a particular data set. Both of them enter the Gaussian prime mechanism, right? Gaussian with trip. So both of them will release an output from a Gaussian mechanism, but one of the Gaussian mechanisms, they will differ both in mean and in variance. Now, what is the privacy guarantee for that? So had this been a theory course, I would have just started deriving something on the board. This is an applied course. So I look at it. And you can see that it is not only that the ROC is not perfect, notice it's asymmetric now. The ROC. Remember, we were focusing nearly solely on symmetric ROCs, where if you have a well-behaved noise addition mechanism and you only differ by the center, then you have two ROCs that are two distributions that are just shifted, and then the ROC tends to be symmetric. Once either the distributions themselves are asymmetric, right, like let's say the Gumbel distribution that is its right side and left side are asymmetric, or the distributions differ from each other, this ROC is no longer symmetric. And in this case, this, for all intents and purposes, epsilon becomes infinity. Like I can't add enough noise to get a reasonable epsilon. Again, this is not a proof for, had this looked good, that would still not be a proof. I need to take a worst case over all data sets, etc. This is also not exactly a lower bound because this is a picture, not a analysis, but okay, we can sample from it and have effectively an auditing process, or we can even compute it analytically or numerically and find out what happens, and turns out that, yeah, privacy is gone. So notice, not only did I not help, I made things worse. Because without truncation, well, I need to add a ton of noise, somewhat unreasonable amount of noise, but still, I add that noise and I get that epsilon equal 1. Here, there's no amount of noise that I would add later, because changing the variance even more complicates things even more. Okay. Attempt 1, bad idea. I mean, good idea, just doesn't work. Attempt 2. Second, let's see what's going on here. Yeah. I think something got mixed up. Sorry. Oh, okay. Attempt 2. Variance is itself something that we can approximate from the data. This is also a linear query if we look at it as just a second moment estimation, right? So the variance can be written as the second moment minus the mean squared. And the second moment also has a range. The range is the range of the data squared. So I can also take my data, privately estimate the mean. Privately estimate the mean and the variance with the very terrible accuracy that I have so far. But still, I get something. Now I can use it. Now it becomes public. I can use it to truncate the data and then compute the mean again. Now this is within the rules of the game. Right? So here's the plan. Mean estimation is a solved problem. It's just utility is not very good. Variance estimation or standard deviation estimation is also a solved problem for the same reason. This is still a linear query. And with the same 10 million threshold, which is bad but still provides some signal, I can estimate the standard deviation as well. So here's an algorithm. Estimate the mean, estimate the variance in a private manner, do a really mediocre job, but use it only to truncate the data, and then compute to get the mean. Make sense? Privacy-wise, this is going to be valid, right? Because this is composition. There's nothing special here. Will it be useful? Well, let's go again through the same process as we saw before. So first, let's look at the ROC. So now, notice, even if I fix the data set, I no longer know how to draw the two distributions analytically, because the distributions now are the distributions defined by sampling the mean from some Gaussian, sampling the variance from some Gaussian, truncating the data based on those estimations, and then resampling the mean from the truncated data. I don't know what's the analytical distribution of this. So here, this plot has to correspond to the auditing perspective that you saw. Remember, in the last lecture, we moved from starting with analytical lines here, things that were drawn because I could call some SciPy function that gave me the PDF at any point, and here I could compute the ratio of those PDFs. And then, once I couldn't, I had to just sample a bunch of times and have some empirical distribution. So this is what we have here. Okay? But this is going to be private. We know that because we have the proof. We did the analysis. We divided epsilon, let's say, by 3 for the 3 steps. We got some ROC. Empirically, the empirical epsilon here is better than 1, but that doesn't prove anything because no one said that we took the worst case data sets. I don't necessarily know how to construct the data sets that will induce the most separated distributions for this particular mechanism. But it's good that epsilon is below my target epsilon, which means, at least it seems like there is no mistake. Right? Notice I could also, I don't need to do it one round, right? I could also divide epsilon by more and then do like one round, have some truncation, compute again the mean and the standard deviation. And on one hand, every iteration was more noisy because I divided the epsilon by a larger number. But on the other hand, I maybe gradually got better. So here's the distribution, the two distributions for repeating it 3 times. What would you expect will be the distribution of that's equivalent to this one? Remember, this is the only one that we currently have that is indeed private. This is the state of the art that we have. Not very impressive by any means. So we're trying to beat this, which is a very low bar. But still, what would we expect it to be? So A, better or worse, and B also, like, will it have some other properties? Any insights? So maybe a hint. Remember I pointed out the fact that truncation basically happens from one side. What kind of truncation basically happens from one side? It's a one-side operation in this particular case. What kind of effect will it have? In words?
It would lower the whatever. It would lower everything.
Conceptually, what that, because lowering or increasing is not the interesting thing, is what type of effect does a one-sided operation typically have?
It pushes to the other side.
It adds a bias. This is not an unbiased estimator anymore. When we added Gaussian noise, or any kind of symmetric noise, or actually not even symmetric, any noise that had zero mean, the estimator remained unbiased. Maybe had terrible variance, but unbiased. Now we introduced bias. So this is what it would look like. Okay, so now this is if we do it 1 iteration, and this if we do it 3 iterations, so let's do it step by step. Black distribution is the generalization error, the difference between the sample and the distribution. Blue is the difference between the correct answer, empirical answer, and the one we released. And as you see, this is significantly biased towards the negative values. Why is that? Because when you truncate large numbers, the only thing you can do is push things lower. But you also have variance from the noise you added. But you push things towards a lower number and then added noise. So you created some bias. So the overall result is the orange line. This one. I would remember to start doing dashed and whatever. So basically this plus this, right? This is this one is the convolution of these two. And what did we get? Well, variance-wise, not as bad, but clearly biased. And if we do it for 3 iterations, slightly different. I don't know if it's better or worse. I don't have a good sense. So this is one family of techniques. Notice what we do here. How many private building blocks did I use in this whole process?
two.
Which ones?
The estimating the mean privately.
What is the building block that I use for estimating the mean? The private mechanism. Sorry?
Yeah, what about it?
No, I'm asking, what is the private algorithm that I use to estimate the mean?
A noise, click.
The Gaussian mechanism.
Yeah.
This is the only mechanism I used here. This entire involved mechanism that I just proposed is essentially repeated, combined application of a single base mechanism with some post-processing. And this is going to be a recurring theme. A single mechanism, or at most a combination of two or three, is typically what defines even the most sophisticated private mechanism these days. So for example, this one has a much more fancy name called CoinPress, and it turns out that you can use it for Gaussian mean estimation even in high dimensions, as long as you have a very coarse initial bound on the ball that contains all the data. You can iteratively do it where you estimate the mean and the covariance, and then you gradually clip things into sort of smaller and smaller ellipses, if you can imagine it, and have some accuracy guaranteed. And for quite a long while, this was the state of the art or close to state of the art, which tells you that not only that combining simple mechanisms with themselves or with each other can lead to non-negligible utility, it can sometimes be even the best we can do. Again, the best we can do under no prior knowledge. Had we had prior knowledge, things could have been very different. Okay. Yeah, so you basically have the hint here to my next idea, but I will save that question. Truncating with the variance has another unreasonable aspect to it in this case, which is as long as the distribution is asymmetric. It doesn't have to be so asymmetric as in this case where you have 0 on one side and a long tail on the other side. Even if it was some value that can be both positive or negative, or that is always positive but the mean is far enough from 0, still when it's asymmetric, truncating by the same distance from the mean is not necessarily the most natural thing to do. What would be a more natural thing to do?
Truncate by distance, which makes the average stay the same somehow.
But then I need to truncate by a different distance from both sides.
Yes, you need to do some privacy on the distance.
Wait, before the privacy, I'm not even sure statistically we can do that. So if you want to truncate such that the mean remains the same, so you need to truncate from the, let's say from the lower numbers much more than from the higher numbers. But if you're truncating in a way that maintains the same mean, you're sort of enforcing, you're basically telling me you didn't hide the piece of information in a way. Right, because you enforce the mean.
We're not trying to hide the mean. We're not trying to hide the mean. We're trying to hide. We're trying to obfuscate the mean enough that you can't get any data beyond the mean.
Yes,
If
but
you can release the whole mean without getting
no, I absolutely agree. But I'm saying I would assume that any type of requirement that enforces the mean to remain about the same value would sort of enforce that the sensitivity will remain about the same. Because whatever it is, imagine two neighboring data sets. The mean differs by some value. Then the truncation must be also significantly. If the mean is significantly different, the truncation must also be significantly different, and therefore the sensitivity remained as bad as it was. So I would assume that would be problematic.
That's when you go for the median, right? The thing is, the closer you are to the mean, the less you need protection. Because the closer you are to the mean, then you need less noise to protect you.
So
So
before median, we can do something simpler. Let's just truncate by the quantiles. So we don't want to truncate by X standard deviations away from the mean because we don't know what does the tail of the distribution behave. But I can always just toss away the first and last 1% of the data. While this, what would happen if I would do that using the empirical quantile? So again, take the data, compute the quantiles. Now I don't need to even compute the mean. Just compute the two quantiles. They have a range. I clip to that, add noise that scales with that, etc. What would happen?
the upper end is much higher, much farther than the lower end, so you've shifted.
Yeah, so it will also suffer to some extent from the same bias. That's for sure. But privacy-wise, what kind of? I don't want to go into the utility discussion before we establish privacy, because if you're not private, it doesn't matter how good your utility is. Once we establish privacy, then let's discuss utility.
Yeah, you wouldn't necessarily be private because if the two databases will be different by like the highest number will be much different. So
No, the highest number will be different. Will probably not have any effect. Why?
but okay, so the second
Not second either. Which one? The one that changes exactly the whatever 99th percentile. Right, so notice it's more challenging. And the first one, where it was 4 standard deviations, we realized that if you change one number, you put a very large number, it changes both the mean and the standard deviation. Now it's more tricky. Change the worst case element, the highest element, that actually has a very small effect. So change the one that's about the 99th percentile point, then you have a big effect. So let's just see what it looks like and take a break. So as you would expect, typical 2 data sets, practically nothing changes. This is what the distributions look like. The quantile didn't change at all. Like because you change one large number by another. Again, trade-off looks okay. But here we chose. So I always maintain this color scheme. The blue ones are the real data. Red ones are if I choosing some engineered synthetic data. So here I chose to put 99% of the examples to be some decreasing order, and then exactly at the 99th there's a jump. So you see here the 99th percentile, the empirical 99th percentile jumped exactly when I changed a single element. Therefore, again, we'll suffer the same problem, even more pronounced. These are 2 distributions that, there is an ROC here that you can barely see. It's basically, you can practically, perfectly distinguish the 2.
The moment that we're doing percentiles of where the cutoff will be, we can actually do a distribution on where the cutoff will be by a percentile question without even actually looking at specific numbers or who's big or
You're
whatever.
saying we will sample what is the percentile?
Yes.
And then, do you know if I can come up with a smart enough pair of data sets such that with high probability, the percentiles that you will choose will be sensitive to this one change? Maybe. And it's a good point. This is how privacy-preserving mechanisms are actually developed. We have the base mechanism. We see that it works when everything's fine. we take one step out of the comfort zone of like a very simple toy example. We see there's a problem. We say, oh, this is worst case, things can be terrible. But they're like, yeah, but the typical case is not. So, well, let's do this mechanism. Well, here's a worst case data set. And then we start playing this game. And looking for the worst case data set, sometimes referred to as dominating pair, this is an essential part of a privacy analysis. Because if you know what that data set is, then you can provide numerical or analytical upper bounds. And like, these are the two worst ones, these are the two distributions induced by it. If I don't know it, I need to somehow reason about the for all quantifier. Okay, so just to recap what we did so far, with mean estimation, we saw that if we don't have a good bound on the range, we're in trouble. We tried empirical truncation of the range, once with the standard deviation and once with the quantiles. We saw that in both of them, that truncation is even more sensitive. It can create a big problem in the worst case examples. In the typical case, everything's great. So we had one technique which was estimate privately the mean and the variance and use that to truncate, etc. And then the question is, will we be able to do other more sophisticated stuff of the same type? Okay, let's take a break. Sorry, yeah?
So up until now, we had to have some sort of assumption about the databases by saying, okay, I click at this point and not in the other one. Mm-hmm. This is the first attempt to not. We don't have to.
But this is a broken attempt.
Yeah,
so yeah,
but
broken attempts without assumptions, that's easy. An attempt that works is more challenging. And I would just somewhat change the language. It's not only do you need an assumption, it's also how sensitive are you to the assumption. So having an assumption is typically easy. There's no way that a person has more money than the number of atoms in the universe, or things like that, right? Like, yeah, well, no. I mean, capitalism went crazy, but not that crazy yet.
Depends on currency.
Okay, yeah, I need to define the units. So you typically can have some threshold. The thing is, we want is how sensitive we are to that. And this is in a way why I chose 10 million. Because if I chose like quintillion, then it will break even if we're like logarithmically dependent on it. And if I will choose something that's very close to the true value, that's sort of cheating. So 10 million is sort of my... So if I have a mechanism that will be okay with 10 million or 100 million and the effect will be negligible, that's good, I think. Because having some threshold, it's not the most elegant thing. We typically would like to get rid of it completely, but we're okay with that. If we're really sensitive to it, let's say linearly in the range, then that's not very useful. Okay, so let's take a break.